Hi, thank you so much. I'm Saloni Jain. I'm a Rapids developer, and I'm a data scientist at NVIDIA. So before I get into the just speeding of machine learning in GPUs, I just want to talk about the whole motivation and the reason why we started doing it. So initially when there was Hadoop, backtrack like maybe 10 years back, everything had to be read from disk, and then you performed your query, you wrote it back to disk, and then you. I'm sorry. Can everyone hear me? I should have started with that. Oh. Oh, sorry. Yeah, I should have started off with that. Okay, I'm gonna start off again. Okay, hi, I'm Saloni Jain. I'm a Rapids developer, and I'm a data scientist at NVIDIA. So before I start off with why we need speeding up machine learning tasks in GPUs, and using API Python, I'm going to talk about the whole reason why we started doing it. And so initially, if you backtrack like 10 years, there was Hadoop where you used to read everything from disk, and then you performed your query, you wrote it back to disk, then again you read it back. And there was like a lot of reading and writing back from disk, and that would use a lot of computational power and time. And then Spark was introduced, and Spark made it much, much quicker. It was less code, and you would just read it from disk, and everything was in memory. But now if you come back, again, it's like nowadays you start seeing issues and bottlenecks with large data sets that we have in just memory processing. So even to do a basic, probably ETL function, you might have a bottleneck in the memory. So that's why people wanted to exploit GPUs, since they have a lot of computational power and they're quicker. But even with that, you would read it from the disk, but you had to read from the GPU and write back to the CPU for other implementations to be used. And so we saw an opportunity here to reduce the read and write back and forth. And just to explain how this would take place, what was the issue, was if you're trying to perform an application A, you would load the application into the GPU. The application would be performed really quickly, but then you had to copy and convert the data so that it could be passed to CPU, and then the application would again copy and convert the data so application B could use it. And then that would be passed into GPU, and so there's a lot of copy and convert that happens, which is a lot of waste of time. And so we looked at if we could just how we could get rid of the whole copying and converting back and forth to improve the time and reduce the computation required. And so what we did is, using Apache Arrow as a base, we created an environment or an ecosystem which would just basically, what you would do is initially read your data in and then perform everything on the GPU. So your query, ETL, and machine learning training, there's no copying and converting between the data. And so once you implement this, you see that you get a lot of speed up. So here what we did is, just to show you how much speed up you get, we created an end-to-end model on the mortgage data set, which was around a 200 GB CSV file. And the whole point of this data set was to see if, to see if someone would default on their mortgage or not. And so we performed basic like slicing and dicing of the data set, and then we trained it using an XGBoost model. And if you see, there's an extreme speed up when you use just a single DGX2, which is a 16 GPU box, or if you use 5 8 GPU boxes, you get massive speed ups. So, but even if you get these speed ups, if you actually have to change your entire code, or you have to learn a new basic core language, like if you have to learn CUDA, that's too much of a hassle and probably not really convenient. So our main objective was to speed it up, but also to keep it within a familiar environment. And so we used the PyData ecosystem and modeled it on the libraries that that everyone's familiar with, like Pandas for data analytics, then you have Scikit-learn for machine learning, you have NetworkX for graph analytics, and so on. So we created cuDF cuIO, which is similar to Pandas API, which is for data analytics. Then we have cuML, which is a similar API for machine learning. cuGraph, which is similar to using NetworkX. And now for cuML, which is basically the library that I primarily work on, I'm going to just introduce it a little bit, give you an idea of what it is, and then we're going to take a deeper dive into Random Forest. So the cuML library, like I mentioned before, is just, it has the similar API as Scikit-learn, and it has GPU-accelerated machine learning algorithms on it. And the reason why we did it is because the data sets nowadays they just keep growing and growing in size. And what we need to do is, if you're trying to just use your data and put it in a machine learning algorithm, it's going to take forever to train. And it's going to be even worse when you're just performing hyperparameter tuning, because that's going to take forever to do. So people tend to perform histogram distributions, dimensionality reduction, and other, like remove the outliers and other patterns and algorithms just to get the data size in probably a smaller contained version, so your training and testing is within a reasonable speed and takes a reasonable time. So just a look under the hood for cuML is that we have a Python, Python layer, and a full-featured C++ layer. And what I would like to specially mention here is we have something called cuML prims, which just contains the primitive mathematical algorithms, which is used for building a lot of machine learning algorithms. So we actually expose these prims, so in case someone wants to do something different and not just use a basic machine learning algorithm, like tweak it up. So you can, instead of writing the whole CUDA code, you can just use these primitive algorithms and go from there. So some of the algorithms that we have in cuML that we actually provide are decision trees, random forest, for classification regression. We have multiple for inference, clustering, decomposition, and dimensionality reduction. But what I would like to highlight here as well is we have something for analyzing your time series data, like Holt-Winters and Kalman filtering. We're also soon going to be releasing, well, actually, next week, we're going to be releasing a 0.11 version, which is going to have a multi-node, multi-GPU versions of a lot of these algorithms in it. And we're working on adding cross-validation hyperparameter tuning to cuML library as well. So now Random Forest. Well, Random Forest is a very famous and a well-liked algorithm in the data science community. And just an introduction to it, in case someone's not familiar with Random Forest, it just consists of multiple decision tree models, and each of these models are trained independent of the other. And each tree is trained using samples that are picked from the training data set, but these samples are picked with replacement. And a random set of the features for these data sets is selected without replacement when you're trying to split at the nodes. And what happens is, since you have multiple different decision trees, which are trained on different data sets, which train on different parts of the data set, it prevents you from overfitting your model, and that's why generally Random Forest is really liked. Sorry, just a second. Sorry. Yeah. So while you're building the Random Forest, the most important part is how you split at the nodes and you create the branches. And while you're creating, you have two choices. One is the feature, which is important, and the other is the split value that you choose. And so generally in cuML, we support 4 split criteria, or the metrics that you would use is Gini index and entropy, which is used for classification. And then you have mean square error and mean absolute error, which are used for regression models. Now, this is basically even used in, but how do you actually speed it up? So in order to speed it up, we have split calculation algorithms, which will help us in accelerating, which is either we can use quantiles or min-max histogram algorithm. And what this does is it reduces the work which is required for the split computation in comparison to just an exhaustive search, which is generally done. So talking a little bit more about these algorithms, it's the min-max algorithm. What happens here is the user generally, while creating the model, will provide us with two important information. One is the split criteria, which was the Gini index or the entropy or the MSE or mean absolute error that someone would want to use. And the second one, which we use, is number of bins. And what happens is a histogram for the features is created, and for each tree node, and the data range for each feature, so the min and the max, is equally split into the number of bins given by the user. And what this helps us do is it helps us to weed out and isolate any of the outliers that would be there. And generally, once you have created the bins, for each bin, we take a potential value, split value, which is generally the maximum value of that bin. In the quantile algorithm, so what we do is the number of bins that are defined is used slightly differently. And first, we're going to actually take all the features and we sort them in an ascending order. And then these assorted and these, oh my God. These sorted features are then split into bins, and each bin, instead of being split based on the features, is actually split based on the number of number of samples. And so what happens is each bin has equal number of samples, but each bin does not have equal number of features in it. So, and then this is a much faster approach than using histogram algorithm, because what we do here is we always compute the feature of the tree only once, which is at the tree node. And so this is much quicker than using histogram, but each of these has a little bit of drawback. So histogram will be more accurate since you keep doing it at each position. And it also helps you weed out outliers. So if you know your data set has more outliers, it makes more sense to use a histogram approach than a quantile approach. So we have a multi-node, multi-GPU version of the random forest algorithm. And what we do here is we use Dask in order to implement it. So first, Dask is actually going to distribute your data to the GPUs. And then we use the training. So then we split the data. So the data can either be replicated and then the same copy is given throughout to all the GPUs, or the better way and the more efficient way of doing it would be to split the data randomly. So you're going to split the data randomly, and the random data is going to be given to all the other, to each GPU to create the decision trees. And when you do that, it's basically the same approach that's taken for creating a normal random forest, where you have the data set and you use the features. While the inferencing here, we perform on CPU, because right now we're still working on the GPU version of the inferencing. But for here inferencing, what we have is a CPU implementation. And so each GPU calls the predict independently, and then you get your predicted results. And for classification, you either perform a voting on the results, or for regression, you're just going to take an average of it. And hopefully, we're planning to release, and we'll be able to release the MNMG for the prediction for MNMG on GPUs in 0.12 release, which is around mid-January. So I mentioned we have a cuML, like CPU version of the predict. So we also have a GPU version, where in order to do that, we use a library which we created called the Forest Inference Library. And this is, since it's an inference library, you can not only just use it for random forest, but you can also use it for XGBoost, LightGBM models, or protobuf, Scikit-learn Random Forest also. So if you have a saved model, you can just a Scikit-learn Random Forest model, and you want to load it and use the GPU for inferencing. You can use the Forest Inference Library, load your model, and use it as well. And here on the side, you can see we have the time comparison. So we trained an XGBoost model, and the model had like 1,000 trees. And we compared the time required for a CPU to do the prediction and the GPU. And you can see that there is a big difference in speed. All right. So now, if you have already trained a random forest, you're like, OK, I don't want to waste time training another one. Because if your data set is too big, you're going to be like, yeah, that's not worth it. So just specifically for random forest, the pickling was slightly tricky. So what we did was internally, we trained the model, and then, or you pass in a trained model, but we convert to a tree-light format. And tree-light is an open source library that we use as a base for our forest inference library. We actually considered creating our own base, but that was another whole, well, it was a lot of work, and tree-light, we experimented with tree-light and worked really well. So we decided to go for it. And so what we do is we create our random forest to a tree-light format, and within tree-light, it has a function called export to protobuf. So the model from tree-light is actually exported to a protobuf format. And once it's exported to a protobuf format in a file, we read the file and save the file data as model bytes. So ultimately, what happens is these model bytes are the ones that are saved. And so when you're actually going to be when you're actually going to be trying to pickle your random forest from cuML, it will read these model bytes, and the model bytes are then again converted to a protobuf the model bytes are written to a file, and this file, since it was initially a protobuf file, it is read as a protobuf format. And then once the protobuf format is read using the tree-light function, it's passed into a forest inference library. And then the forest inference library performs a prediction, and you get your results. Even though I know it's a lot of steps, but there is almost no difference in time. Okay, yeah. So this is one of our notebooks on GitHub. And this is just going to talk about the random forest classification and pickling. Okay. So one important thing I want to show here is how easy it is to use cuML. So from Scikit-learn, like if you see the way we import it, oh my God. Oh, I'm sorry. I thought that was actually on. How do I? Oh yeah, no, but how do I go to this? But, oh no, but this is Chrome. This is not in my presentation. This was a link, so I clicked on the link.
Can you escape go back
Oh,
and share?
the screen? Okay. Sorry about that.
Yeah.
Okay, yeah, much better. All right, so here what I wanted to highlight is, because I actually don't have time to run it live, but the important thing here I wanted to highlight is how easy it is if you already have code which is using Scikit-learn to just use cuML in it. Is when you're importing is right here, it's Scikit-learn ensemble random forest classifier. And for cuML, it's the same thing. All you have to do is replace the sklearn with cuML. And we have, well, we're loading here a data of 2 raised to 17 size. And we create, so this is just based on random forest. This is just using random data. So you just use a scikit-learn's function, make classification, to create the data set. And right now we're going to pass through a random forest classification model, and I'm also going to show you pickling. But yeah, so this is the host, you train it, and when you have the time, you should really just go to this function, and you should try the notebook, because when we ran it, scikit-learn takes, yes? Oh, sure. Is that better? Do you want me to go to the top? No, okay. So here, the scikit-learn model, we're creating like 40 trees, and you have each trees of a depth 16, and you just set a random state. And you'll see it takes minutes to run the scikit-learn model for this data set. But when you're actually running it on cuML, it runs in a few seconds. And we've kept everything the same. And also for prediction, when you're actually doing pickling, it's the same pickling you would be doing if you were actually just pickling a scikit-learn model. There is no difference at all. So you would import the pickle, you would do pickle dump, And so you can either dump it into a variable, or you can just create a file name and you can dump it into a file name and then read it from there. All right, and I'm going to go back to the presentation. Okay, so now some of the trade-offs of using cuML over scikit-learn and some of the limitations that we have. So first of all, when we perform pickling, and you perform pickling for random forest regression models, since we're doing it in GPU and we have a lot of parallel processing going on, the results aren't always exactly reproducible. And what I mean by that is if your test case has 10 samples in it, so 9 of them would be exactly the way it was for the previous model. But when the 10th one would be slightly off due to parallel processing. And in random forest classification, right now, Forest Inference Library just supports binary class classification. We're working on multi-class classification, but it's still a work in progress. And the best way to get the most out of cuML would be if you have a larger data set. You can really see the time difference when you're using it when you're using scikit-learn on it or when you use cuML. And the second one is using fill for regression, so Forest Inference Library for using prediction on regression models. It's amazing speed up. And even for binary classification, it works really well. And the next one I would say is when the split acceleration, the split algorithm used for acceleration, if you actually use, if you know your data set and you know you might have outliers in it, it makes more sense to use a histogram algorithm in it. But if not, the quantile algorithm is much quicker, and there is very little difference in accuracy if you see. And right now, we had released our 0.10 version in October 2019. And like I said, we have our 0.11 coming next week. So, well, these are some of the features that we have. And we have added a lot of M&M multi-node, multi-GPU algorithms for the next release in. And somewhere, like hopefully in March 2020, we hope to be done with the multi-node, multi-GPU versions of almost all algorithms, other than a few. And if you were interested in using Rapids, it's super easy. We have a GitHub. It's all open source. We have a GitHub link. We have a GitHub page which has all the code in there. We also, if you don't want to build it from source, there's Conda packages that you can just do Conda install for. And we also have Docker Hub containers. So if our main website is rapidsai.com, and if you go to that, and you scroll all the way to the bottom of the page, this is something that we created which would even make it super easy for you to pick what you want and to install them. Because I have used a lot of libraries when I was studying, and always setting them up was a big pain. Like setting them up, getting them working, always was a big pain. So we've tested it, and you just do that, and you have it in your environment. It's super easy. And if you are more of a container person, then Docker containers are also like, if you select that, it'll give you instructions on how to do it. This is our Rapids AI page where we have all the code there if anyone's interested. And we also have documentations at docs.rapids.ai where you'll be able to see the different variables you can use. And we have tried to keep it as similar to scikit-learn as possible. But there are, since we do perform the process, or we do implement the algorithms in a slightly different way in order to speed it up, there is slight variations, and we do have additional variables, or there are certain variables that we do not support. So I would definitely suggest going to the documentation and also reading that. And then it's, like I mentioned, it's all open source. So if you're interested in contributing, you can always contribute to Rapids, or these are some of the other projects that you could contribute to and help. Thank you.
Questions?
Thank you. Very interesting talk.
Thank you.
Just so I'm clear, the Docker containers that we could experiment with, do those actually provide any GPU resources? If you don't have a GPU of your own machine, right?
Oh, yeah. No, you need a GPU for the Docker containers,
Yeah.
but yeah, you're going to need a GPU for using the Docker containers.
Okay.
Yeah, sorry.
Forgot my question.
It's okay.
I saw that the inference time using the GPU library is like 34 times faster.
I'm sorry, could you repeat?
The inference is 34 times faster using the GPU library using
Oh, for the
cuML.
XGBoost?
Sorry, yes.
In the XGBoost form?
Yes. But the problem with using GPUs during inference time is they're really, really expensive because most of the companies would want to deploy something on AWS or Microsoft or Google. So do you think there is some parity between, or there is some incentives for companies or data scientists to use GPUs for inference instead of CPUs just because of the cost it takes?
Well, this is not just for this is for inferencing,
Yeah.
and this speeds up inferencing, but we also have, like, for training, so we have XGBoost and different models that you can use for training. This is more like if you've already trained a model, and you don't want to waste time training it all over again, right? So this
Yeah.
is more like in the pickling format, that you can just take your model and then use it for inferencing.
Okay. Cool. Thank you.
Does that answer your question?
I think so, yeah.
Okay, cool. Oh, right there.
So, what about older platforms, ones that are disconnected from the cloud? Do you have solutions for that? Like old machines, old clusters? I'm asking for a reason because those still exist.
So just disconnected from cloud?
Yeah. It's things that work outside the cloud, like things that even don't have Docker. Can you help those?
Well, so you're gonna have Conda, right?
Yeah.
So we have Conda, so we have packages for Conda. So it's literally Conda install cuML or Conda install cuDF. So you can use those to create your environment. So in the last slide, just a second, I'll just show where it'll be easier. Oh, right there. So, you can, I'm not sure if you can see, but here we also have Conda. This is the Conda install. So if you can just easily pick which version do you want. So we have two versions, which is stable and nightly. Stable is the released version, and nightly is the one that we release like every night. We update the containers for the current developing code. So it's like if we're working on some model and you want it, you can go to the nightly one and get it. And you just pick your packages, and that's a Conda install that you have. So you don't need a container to actually play around or use Rapids. You can just create an environment on your system, do a Conda install. You have everything there to do it.
One second, I have a question myself.
Yeah.
I have a laptop which doesn't have a GPU, it just has CPUs and multi-core CPUs. I would like to write ML code with with cuML and all this stuff, but just simulate the running using a GPU, just simulation, make sure everything runs properly end to end, and then I can fire up some instance which has a lot of GPUs, and then make sure that just run it there without any issues. I don't want to be experimenting and failing and experimenting in GPU, expensive GPU instances. Do you have any kind of simulators available, or how do you experiment?
Oh, for just using CPUs?
No, using CPUs, but it should be
like you should
GPU
be
code.
able to use the GPU code
GPU
on
code.
CPUs?
Yes, exactly. Is there some kind of simulator which will basically run end to end, and then I can blindly
Not
copy it and
I'm aware of. I don't think so, but I can double check it, and then if you, I can talk to you later, and then I can let you know.
Hey,
Yeah.
we have these famous packages for data processing, right? Like NumPy or Pandas, right? So that is traditionally used for all the CPU processing. So when I want to adapt my code to QML, say like, you know, do I have to rewrite my code, especially for the data processing steps, to adapt to the processing in QML?
Sorry, that was loud. No, so like I said, we try to keep the API similar. So all you would have to do is, like in case of Pandas, if you want to use cuDF for like ETL processing, all you do is just replace the PD like with the cuDF, and that's it. And for cuML, you replace your Scikit-learn wherever. So if you do import Scikit-learn, and then you have like random forest classifier here. So all you have to do in order to use it is just replace where you have Scikit-learn being imported to cuML. So you just change one word, and that's pretty much it. Yeah. So for most, that should be it. And like if you want to see, like if you want to do some other variations, like with the cuML model, then you can see the documentation to see what all you can add to it. The ETL, right? So pre-processing of the data?
Pre-processing of data, making the data ready for the model in itself like takes a lot of time, right?
Yeah.
So how do you handle that? I mean, do any of your packages do that?
Yeah, so cuDF is similar to what you have for Pandas. So that's for your pre-processing, your ETL, what you do, like what you mentioned, right? Like the whole cleaning up, anything that you want to do on that. So before you actually add it to a machine learning model. So all of that, what you do with Pandas, you can do it with cuDF. We have similar API for that, so you can just replace Pandas with cuDF, and you should be good.
Hi. My question was, what does it take to extend it? So if you wanted to implement your own like random forest classifier, are you writing CUDA, or is there a simpler way using the kind of the cuprims?
The cuprims.
Yeah.
So cuprims basically would give you the basic mathematical requirements that you would need. But there's also, like, since cuprims is in C++, so you would need to do C++ a little bit of it. And so in that, we don't have everything exposed to Python. We just have the general ones that are used, like probably distance algorithms or like some of the normal linear algebra that's required. Random forest is much more complicated. So for random forest, you would have to, if you want to change it up or do something else, you would have to do it in C++. But for others, since which have the general ones that are required in a bunch of machine learning algorithms, we have those exposed. But for the others, you would have to do C++. So you don't need to do CUDA, because you already have it in prims. So you need to do C++, but you don't need to do CUDA programming. Yeah.
And the other question was, I know Numba can target GPU. Is there any planned intercompatibility with that to be able to bring something like a GPU kernel in?
So for in cuML models, we do support Numba, CuPy, NumPy data that you can input as. So we support, and we support cuDF, of course. So all of these data sets are supported, and yeah.
Any other questions?
Okay.
Yeah.
All right.
All right then.
Thank you so much.
Thank you very much, Saloni.